So hello again. It's not common, but this time I decided to actually do a presentation myself as well, to explain, to better place why the AIR Center has so much interest in Julia and in particular in this community. And I titled the presentation "Challenges, Opportunities for Data Science and Computation." And you may wonder why data science and computation, two apparently different things, but they're more and more convergent, and the interaction between the two is more apparent than ever. So I'm going to talk a little bit about the AIR Center, just a very brief introduction, then talk about the opportunities that we see and the challenges that we face as well. So the AIR Center is, as I said earlier, it's a non-profit organization funded mostly by the Portuguese government, but has a lot of partnerships around the Atlantic. We are part of the United Nations Environment Program. We are a grid node, so we source data to them. We are an ESA lab, so we have our technical team works in close collaboration with other European Space Agency laboratories. We are part of the National Scientific Network for Computing, and so through that also for part of the European Computing Network, and the Marine Biodiversity Observation Network, the MBON, which is based in the US, but we have the World Secretary here we've had for the last 4 years. So starting with the opportunities that we see, I think nothing speaks higher than the Nobel Prize this year, a Nobel Prize for protein structure prediction, computational protein design, that was won by David Baker from the University of Washington, Seattle, expert on the field, but then by Demis Hassabis and John Jumper, who are experts in actual data science and machine learning. And so this is just an example where we see that, this is an example of the opportunities that data science has at the moment. You name a field, name a topic, and data science can probably help. And in some cases can make a huge difference, as is the case here. And another important aspect of this is that machine learning is not something of researchers anymore. This chart is pretty obvious that the transition, so there is a growth, yes, great, but there is also a growth in the industry. Data science, or machine learning specifically, AI specifically, is reaching the public. It's in the industry. It's being used increasingly in the industry. So in other words, it has an impact, it makes a difference. And we are using it as well. We are very small. We have around 20 people, around 12 technical team only, in several areas: the ocean, space, and data science. And I'm going to go through some examples of our work, very small examples. We are also very young. We have 5 years old. The AIR Center is only 5 years old. And these are examples where we use data science to help local communities and local economies. And the reason I'm talking about this is to help establish bridges here so that you know what you're doing, we know what you're doing, and we can find more bridges for collaboration. We always work, this is in our DNA, always work aligned with Sustainable Development Goals. And these are the ones, these 10 are being addressed right now with the projects that we have going. So an example of support, as I mentioned, local communities, in this case a municipality here of Angadui region. The city center is protected by UNESCO. You cannot put solar panels on the buildings. So they also don't want to compromise that and compromise the possibility of the residents to have access to this kind of technology, of clean energy. So they asked us, we need to install create a solar farm, we need to install it somewhere on the island, where should it be? We went to 10 years of solar radiation, measured by satellite data, and we gave them a map, produced a map of actual radiation on the island, radiation levels, and they can now make an informed decision. Supporting livestock producers, cutting a very long story short, there is a fungus in the pastures that sporulates with certain meteorological conditions, and then the cows ingest that with the grass, and that has very nasty health effects, leads to permanent damage on the liver, sometimes death, and sharp reduction in the amount of milk produced. And so we created a data pipeline that analyzes data in real time and provides alerts to the farmers in real time. So every hour they can check what's the status, what's the level of risk in their pastures, and simultaneously we're doing collecting samples and checking what's the reality to do the validation, what's the reality in fact on site. And based on this data now, we can improve the algorithm and the state of knowledge of science based to have a better, an even better prediction algorithm to measure that measures the risk. Supporting farmers as well, vineyards, health. There is a small economic aspect to this too. The vineyards here on the island, they are not new, but there is an intention to increase them, and the farmers don't have a lot of data about how diseases that affect the vineyards progress and affect the vineyard here in this weather, in this climate, with this soil, etc. So then we set up a project, and we're giving real-time data as well, information about the risk of health for the vineyards. And then finally, for fishermen, so these, as you see, these are all local and very important community projects that's supporting local communities and local economy. In this case, fishermen, this project increases the operational efficiency and pollution avoidance. So it's the system is called Custodian. It's a set of it's a data pipeline with hardware as well that we built in the last 2 years with a project that allows fishermen to put specific sensors for location on the fishing gear, on the buoys. So they always know where the buoys are if they are it reduces the chance that that equipment is lost in the sea, and also helps them recover them faster. So they lose way less hours, they use way less fuel, and they have more income because they don't lose so much gear, which is quite representative for them. 10% a year in gear loss reduced. And at the same time, reduced pollution in the sea and the ghost fishing by having nets lost in the sea. The last project I'm showing now, supporting scientists and the industry now in the ocean in general, in terms of global monitoring of internal waves. I'm not going to talk much about this because there will be a presentation in the afternoon specifically about this, but that's just a very new project that we started with some funny twists that you're going to hear about. But again, supporting scientists and potentially some parts of the industry. So now data science and high-performance computing, the age of AI. So computing is a universal tool of science and engineering. I mean, and this is aligned with data science, puts it right in the center of what's, at least to a lot of people, is very interesting today. We can do simulation, data analysis, AI. And to make sure that the greater community around the Atlantic has access to this infrastructure, we're creating something we call the Atlantic Cloud, which are basically shared infrastructure. We have our little data center here, so Brazil, LAMS, and other institutions in Brazil have joined have helped us to create an hybrid cloud. So we join efforts from different places. We joined all this infrastructure with a single point of entry, and we can have several institutions using the same resources, maximizing, optimizing the use of those resources, and following that also a lot of practices and standards for data storage and data handling, etc., which is really important too. It's not only have data, we have to work at the scale of the Atlantic, for example. We have to measure things the same ways and have data stored in similar manner, etc. So that helps us work together, basically. So we aim to have a lot of infrastructure spread throughout our partners, so throughout the Atlantic. At the moment, it's only here in Terceira, Portugal, and in Brazil, in 2 institutions. And one thing that we installed here out of necessity was a IoT network, a LoRaWAN network, a set of antennas, gateways, and then you can put a lot of sensors on that network to read real-time data. We're using this for several projects now, most of the projects I mentioned before. We had really good results. We even published a paper about this, and we are expanding this throughout the islands in the Atlantic, in the Azores and potentially in other parts of the Atlantic, coastal areas and islands. This LoRaWAN technology is super low cost, low bandwidth, but also very low power, which means that each sensor the battery for each sensor can last 1 or 2 years. So now to the challenges. The main thing about the challenges are energy and environmental footprint, and of course the costs associated with the infrastructure and the energy that it uses. We see computing efficiency as a paramount thing to deal with if we want to be responsible. We're doing data science. We want to do data science at scale in the sense that not to run large LLMs, but in the sense that we want to run ocean modeling, for example, regional models, etc. And we need to be responsible. After all, we are a member of the United Nations Environment Program, and we make sure by our decree internally, we have to work to pursue the Sustainable Development Goals. So we cannot say one thing and do another. So that's one of the reasons Julia is so important too, because it's a language that, in principle, it can be more computational efficiency, so power efficient. We see 3 areas in which there is a lot of work to do, and some of them have a lot of potential. Software. Potential increase in efficiency by over 1,000%, probably way more than that. And Julia can be a big part of that. You, as developers in Julia, can have a huge impact on the power efficiency of computing. Then chip architecture, potential increase by tens of percentage points. Probably a large impact as well. It's something that, unfortunately, I mean, the Air Center is not aligned with this, and probably we're not going to be working on this. Also, Portugal is probably not the country to do this kind of work. And then we have data center setup. So potential increase in efficiency by 40%. That will be neat because that's how much data centers use. So 40% of the energy data centers use is just for cooling. So it's not for the essence of the data center. So in terms of software, we can do better code. We can use better algorithms. We can create new and improve the ones that we have. We can use better tools. A lot of people, for example, one of the things I like about Julia is this coherence that you can do Julia, turtle after turtle, all the way down. You could be Julia. You don't need to resort to other more performant languages. When we use Python, we really like Python is nearly an API most of the case to then for C or C++ or Fortran in some case. So using in a lot of instances very old code and probably not always the most efficient way of working. And this is somehow troublesome when we put things in production and we want to use them minute after minute, year after year. But the problem here we find is it's not really sexy to do the same thing just better, right? So we find it hard to get funding to do, to just rewrite the same or similar algorithm with different tooling. This is part of the reason why I personally appreciate so much of your work, because you believe in something and you just go and do it, and through that personal effort, you end up creating, in the long term, a more efficient system overall. But if we could create projects to identify some bottlenecks and convert this to Julia or whatever tool. I mean, we don't use only Julia, we use everything, and but we try to use efficient tools. And we always strive to use the most efficient tools for the job. For example, APIs, we do Go. Everything that's really hardcore for a lot of thousands of users potentially, and has to be run really fast, has to have a good environment for development, we use Go, yeah, sure. But for the science part of things, we try to use Julia as much as possible so that you can have the scientist all the way through the user. And you don't have this throw it over the fence problem, and every time there is iteration, that takes a lot of time, and there's a lot of, gives a lot of headaches to everyone. So we see that Julia has a huge potential in this arena. So that's part of the reason why we are organizing the JuliaEO for 3 years in a row here. If you're here, no need to scan that because that's to register to attend online. So in terms of computing efficiency in terms of hardware, we have to look at other architectures. That's as much as here at the Earth Center we can do. We're not going to build new chips or anything like that. We're not going to be involved in that in any way. But we can look beyond x86, which occupies way over 90% of all computing and all data centers. We're looking at ARM, we're looking at RISC-V, we're definitely looking at GPUs to increase our efficiency, and in particular energy efficiency. So why GPUs are so important? Because they allow us to do several things at the same time. So with the same amount of power, or sometimes even way less power, you can do many more tasks. You can do different tasks, you can do all sorts of tasks, you can do simpler operations, but the instruction sets for GPUs are also growing a lot. So GPUs are definitely a way to increase the efficiency of our code, and we should strive to do that. And that's another advantage of Julia, because it allows you to do that in a much simpler way and proper. And this is specifically useful for Earth observation, because original GPUs were created for matrix operations and for displaying and for ray tracing, etc. So doing the same operation many times in the same operation simultaneously in many cells really fast, because it does the operation in many cells at the same time. And so it's way more efficient. And if we compare the gigaflops per watt, so the work versus the energy, the electric, we can say the electric energy uses to do that work. GPUs are way more efficient. So if everything we can give to the GPUs to handle, we should do that. So now come to the third topic. We talked about software, we talked about the hardware part, and we talked about the data centers. I mean, and data centers are great. We have one. I mean, we love it. Our data centers work like in the limits of physics. They have for a while. We keep expanding that. But they're also not great because they use 40% of their energy just for cooling. 40%. I mean, we could do 40% more compute or use 40% less energy, right? And in a world where you're using so much energy already for this, like 2% of the global electricity usage is for data centers. It's over 1,000 terawatt hour of energy. That is significant, and we can't ignore this anymore. In fact, one of the limitations for more compute, and nobody sees the amount of compute in the world reducing, it's the availability of energy. So, for example, Singapore created a moratorium on data centers in 2019. So they said, well, we don't have land and we don't have energy for this kind of thing, because a lot of companies were creating data centers there as like a hub for the Asian market. And so they put a stop to it. Microsoft is reactivating a nuclear power plant to power an AI data center, specifically AI data center. So for those who don't know, AI consumes even more energy than traditional compute. Amazon, Google, and OpenAI are investing in nuclear power. Current construction of AI data center in the US are adding a load of 75 gigawatts extra to the grid in the short term, which is around 600 terawatt hour per year. This is equivalent to the energy that Brazil uses in a whole year. Brazil is a huge country with a population of nearly 300 million, right? From now on, we're adding this per year, and might get worse. So it's not negligible, the amount of energy that's being used, and the fact that data centers could consume 40% less if they didn't need cooling or did cooling in a different way. It's very significant. And this is something that we believe that we could help with. So we created a startup called @Depth that is a spin-off of the Earth Center, and we are mentioning this publicly for the first time. So this startup I started working in this in March last year, more or less, like on my own time. And I just went back to basics. Like, so what's the problem here? You have electronics that are generating a lot of heat. What's the best way to extract that heat? And it turns out that if you think about it properly in terms of basic physics, right, you're blowing air to that. I mean, air is actually a thermal insulator, right? So it's probably not the best way to do things. And then in order to get more efficiency or more capacity out of the cooling, we add more speed to the fan. So we spray the air with higher speed, so a higher rate. And so if you walk into a data center today, like just the noise of all those fans working is incredible. And you know that 40% of that energy is just for that, 40%. So we started doing things from basics very differently. And so we're trying to create a next generation cloud. You know, as Marco just said, 95% of the startups fail. But we're happy to be working with them, with the UT Austin Portugal program. In particular with the Texas Advanced Computing Center, which when I visited in September, they are very into, and they have been for a while, into ways of doing more efficient computing, in particular immersion. And so we are using also that technology. And I'll go into more details later. So our vision is a world where cutting-edge computing power and environmental sustainability are in harmony. And our mission is to accelerate that process, whatever means. And so for that, our main goal is to eliminate the waste of water and energy. I didn't mention water before, but data centers consume a lot of water as well. So we want to reduce the ecological footprint of data centers and create a security first cloud for data and model sovereignty. Because it's another problem. Data centers are not like 8,000 all over the world, but if you want to choose where you want to put your stuff, there's always a lot of limitations, and your data and your models normally end up elsewhere in places that you don't necessarily want or not on your country most of the time. So our approach is to create small compute clusters distributed throughout the world, with 40% low energy consumption. So we go for power user efficiency 1, which is the best you can have. So all the energy you use is for compute, not for cooling. Data and model sovereignty, because there are so many, there's relatively small clusters. You can, and they are modular, you can make them larger or smaller depending on the needs and the potential of the site. And you can put it in your own jurisdiction, most likely. We can also have, because our cooling system is so efficient, you can have extreme compute density, extreme power, equivalent to a rack with 400 watts, which is like 10 times more than what a medium rack is today. And we also have far lower capital expenditure. And it's modular and scalable, and it also allows for really fast deployments. So we use this kind of solution where you have in ports where there is already security, there is already network, and there is a lot of power available, and you can plan long term. We're installing these small pods with more or less modules or pods. And the cooling system is simple. We're using immersion, which some data centers are starting to use as well. This means that the server is itself inside of a liquid, and so the transmission of heat is virtually perfect to the box, and then the box directly to the ocean. And this results directly in minus 40% of energy consumption, so minus 40% of carbon emissions. And if you're worried about warming up the sea, I mean, that's virtually impossible. The sea is actually, the ocean is the planet's heat sink. And you have, because this is modular, in some ecosystems you might be able to put one module only. In other places you could put 1,000 or 10,000. Of course, our goal is to not harm the ecosystem. But by default, we're already reducing, imagine, 40% of the carbon footprint. So here you can have, so these are part of our own data from the first tests. On the left-hand side, you see the traditional air cooling, where you have so the spikes in pink, the spikes, I was running benchmarks to take the processor to the limit. And so the processor runs on a baseline, a thermal baseline around 60 degrees, and then goes to 85, and 85 is cut by security, so it's throttled down so that it doesn't burn. So you also lose some cycles there. And then once you immerse it, the temperature baseline is reduced to 30. You have a much smaller delta. And no matter how long you run the benchmarks, you never go over 44 degrees. And this is passively cooled. So no energy for cooling. The energy is just used for what it meant to be, which is what we want, the compute. So water consumption, we use 0 water consumption. Data centers in general use a lot. So a reference here in 2014 alone, and this was quite 10 years ago. the amount of water used by the data centers in the US alone is enough to irrigate an area equal to Germany and Poland combined with 1 centimeter of water. You could cover 2 countries, large countries, with 1 centimeter of water. This was 10 years ago. Or you could hydrate the entire population of Africa and Asia for 1 year. So again, and this is normally good fresh water, so again, not negligible, and our system does lots. So it's very hard to find really good data for a long period of time about data centers, but we found some good data for Germany for this period 2010 to 2017. And the summary here is that of this plot is that if Germany had used our solution for all their data centers, they could have run their data centers with the same energy for 4 more years. And they could have saved hundreds of tons of CO2 emissions. We're not saying that our solution is going to replace data centers, not at all. I mean, we're going to be in the edge, we're going to have small clusters. It's not the same, but it's a complement that it's moving in the right direction. So the offer will be virtual machines, containers, all the normal offer, but in a zero trust security network. And that's not easy to find nowadays. And ours is built like that. It allows most companies or countries to have data and model sovereignty. You could have things where you want them because this is built to put in ports, to install in ports, or if you have a flowing river or a large lake, you can have this in your backyard if you wanted. You could have this as a private cloud if you wanted, or you can have this as a normal or a public cloud, our cloud. And you can have extreme density. Serious density, you could have up to 10, well, at least 10, but probably more. 10 kilowatts per 1 unit, one server. In water up to 35 degrees, so that's like the highest temperature water in the sea, and that's like in the Singapore area, for example. You could have these. It's also secure. Actually super secure by design as well, because it doesn't have, once it's deployed, there's no human contact possible. There are sealed boxes underwater, so nobody can go there with a USB flash and stick it on and do something you don't want to happen. So if it's working, if it's deployed, there's no human access, only via the cloud, only via the infrastructure. That's really thumbs up for security, but also you can have systems like if something really strange happens, if something once goes there with a submarine and tries to get it or something, we control, we have a lot of sensing on this pod, and so we could just inundate it, and the replication, it replicates automatically by the cloud in other places, and just all data is lost and it's recoverable. So if somebody will take something, it will just take metal, basically. And so a lot of operational advantages, carbon emissions are much lower as well. So this is all I had to say. So in summary, I mean, the Air Center is working normally with local communities. We believe in Julia for all these reasons that I mentioned. We're working in the software part as much as we can. We're a very small team, but we organize this event and we're spreading the word on Julia as much as we can. Now we started a project with Nigeria, for example. And so we don't have a lot of resources, but we do the best we can. And all the resources we get are for this. So software. This is the front. We work on software. We're not working, or we don't see that we could do any contribution on, or Portugal could do any contribution, or most countries, by the way, on chip development and chip fabrication, etc. But on the data center side, we could. And this approach is great when you think about the Air Center spreading data centers across the Atlantic and reducing in a responsible way, let's say. I mean, the most responsible way possible. So thank you. That's all from me. Super glad to have you all here again. And you won't hear from me more in terms of content, just for like logistic stuff. Now it's with Adriana Ferreira. She works at the Air Center. And so this presentation is going to talk about now the internal wave service, something we're starting now too.
Okay.
But after lunch, it's no more Air Center. It's just about you. And all the other days are just about you.
Okay. Hello, good morning. My name is Adriana, and I'm a maritime applications developer at Air Center. My presentation is about internal wave service, which my data science team and I developed, and we are still developing. I will start by introducing internal waves, and then João Gonçalves and JuliaEO will talk about the algorithm and used in this service. Purpose and overview. I began this presentation by drawing an analogy to a book based on a true story, Moby Dick. In this book, we find the following quote: "When beholding the tranquil beauty and brilliance of the ocean skin, one forgets the tiger heart that pants beneath it, and will not wringly remember that this velvet paw but conceals a remorseless fang." Indeed, the surface of the ocean can conceal what lies beneath it. In Moby Dick, referring to the giant white whale that in the end overturns the vessel. A perfect analogy can be drawn to the lesser-known internal waves, which, hidden within the ocean, are often much larger than surface waves and play several critical roles in the ocean, from transporting nutrients to influencing the global climate or damaged structures. But what are ocean internal waves? One way to introduce them is by imagining them within the ocean, occurring between two layers of different densities along the Pinelo line or thermocline, often with larger vertical amplitudes than surface ocean waves. They can reach more than 100 meters. The movement of internal waves generate orbital particle motions, which at the ocean surface form slick bands that make them visible both to naked eye and in satellite images. In this photograph, in Cape Cod, we can see the rough and smooth bands of an internal wave. Here we have a graph that is illustrating various ocean phenomena and their temporal and spatial scales. Near the middle, we have internal solitary waves, and the arrows point to recent studies of this phenomena, which propagates over a space and time. For example, in case of Meng et al. 2022 and Magalhães et al. 2016, the waves propagate over long distances, 1,000 kilometers, and can last up to a week. But why are they important? Internal waves are crucial to understanding ocean dynamics and their broader impacts on marine ecosystems, climate, and human activities. Here are the main reasons why they are important. They transport energy, which can give rise to other ocean phenomena. They contribute to mixing, redistributing heat, nutrients, and gases between the ocean layers. Internal waves are one of the main phenomena contributing to vertical mixing in the oceans. They transport nutrients by promoting mixing. Internal waves transport nutrients from the deep ocean to surface layers, fueling primary production. These processes support marine food chains and biodiversity. They contribute to climate regulation. Internal waves contribute to the ocean's role as a heat and carbon sink by facilitating the exchange of heat and gases between layers. Their influence on ocean circulation impacts the global climate system. So they have a connection to global ocean circulation. By influencing the mixing and transporting of water masses, internal waves are connected to the thermohaline circulation, which is a major drive of global climate systems. They can also make coastal impacts. Near coastal areas, internal waves generate upwelling events that bring nutrient-rich waters to the surface, enhancing the productivity of fisheries. They can also contribute to coastal erosion or sedimentary suspension. and they can influence engineering and submarine operations. Internal waves create strong currents and turbulence that can affect underwater structures like oil rigs, submarine cables, and pipelines. So, internal waves are essential for understanding the physical, chemical, and biological dynamics of the ocean. And where can we find internal waves in the ocean? This is the most up-to-date internal waves world map that I'm aware of. It was created using MODIS images collected between August 2002 and May 2004, manually. While I know it is missing some hotspots, such in the middle of Pacific Ocean, it remains very complete. The red dots represent the mass centers of the internal waves in the ocean. Our goal is to support researchers by delivering detailed analysis of internal wave hotspots, thereby improving our understanding of the Earth's oceans. How? We created the Internal Wave Service. The data we are using for now is from Sentinel-1 that operates in SAR mode and therefore is not affected by clouds or atmospheric conditions. This is optimal for regions where clouds are common, such as the Azores area. At the moment, we are using the wave mode, which operates primarily over open oceans with VV polarization. It captures 20 kilometers by 20 kilometers vignettes at a resolution of 5 meters, acquired at a regular 100 kilometers interval along the orbit. However, Sentinel-1 wave mode does not operate over the entire ocean. For instance, in coastal zones, the satellite typically uses other modes. In the future, we plan to add other modes and other satellite data to our service. This synergy will allow us to calculate relevant parameters. But what is this service? Every day, the system processes all the images and applies our machine learning model. The model classifies the images as either containing internal waves or not. Images without internal waves are deleted, while those with internal waves are added to our database. This greatly facilitates the work of researchers who previously had to manually analyze thousands of images to identify a positive case. Here above we have some examples of internal waves, and below without internal waves. Below the first images is wind patterns. The second image, it's a boat. The third image, it's a rain cell and a thermic front. And the last one is a thermic front. Which machine learning model do we use? We tested some machine learning models and created a competition on the Kaggle platform. To support this, I manually labeled nearly 1,300 images. The winner was Gilberto Jr. from NVIDIA in Brazil, and we had the pleasure of personally presenting him with the prize. We are currently implementing his model using the new dataset we have, which consists of the images saved by the algorithm. At the moment, we are supervising the results using the validation platform. I am the expert handling this task, but in the near future, we plan to have more experts assisting with it. In just 3 months of the data, we have more than 1,000 images classified as positive. For every positive image, we keep one negative image to ensure balanced examples for retraining the machine learning model. Here is an example of an internal wave classified as positive. I have no doubts that it is, so I confirmed it. To bring together internal wave experts and improve this service, I'm excited to announce that the Air Center, in collaboration with University of Porto, is organizing a workshop with specialists from various fields. We already have confirmations from these institutions: IFRAMER in France, NERSC in Norway, the University of Southern Mississippi, and CIMAR in Porto. If you are interested in joining, please let us know. Now, my colleagues will present the program and the model we are using.
So, these images that Adriana was talking about, they're used to validate the train model, and will be used to train the model after the code created by Gilberto. is integrated into our existing code. And I will now show you the winning model and briefly explain what it does and pass over some of the lines. So basically, this is a binary classification task that, as we can see here, achieved a quite high high score. There's obviously some steps before this, but here we have the data loading, and we can see that an extra column is created to add the full file paths of each image. But skipping to the custom dataset class that handles the images, here we can see, for example, that uses the image open to load the images and then convert them into RGB. Then it is used the TIM library to load a pre-trained deep learning model. And we can see that the images are then standardized and resized to meet the model's requirements. That model is then moved to a GPU and set to evaluation mode for inference. That inference is divided between training data and test data, respectively. As Adriana mentioned, she manually labeled 1,300 images, half containing internal waves and the other half without internal waves. After augmentation, that number increased to approximately 5,000 images, and out of those 5,000, 70% are used for training and the remaining 30% for testing. Here we can see that the code defines the data set in the data loader at the beginning, for this case, for the training data. And then it uses the pre-trained model to generate feature embeddings for each image. Then there's a loop, a batch loop that appends the processed features from each batch into a list and then combines it into a single array, and pretty much does the same thing to the test data. Then the code defines the XGBoost parameters. There's a bunch of them, but also a way of optimizing the performance by using a GPU. And then the model performance is evaluated by a cross-validation score. We can see that Gilberto used the area under the rock curve metric, but also the stratified k-fold that provides the train test indices to split the data in train test sets. Here we have one of the outputs, which is the validation score. We can see that it's quite high, which means the model has an excellent performance. After the cross-validation, the XGBoost model is trained on the entire training data set. We have the features and the labels, and then predictions are generated for the test data. Basically, for each image, for test image, that function predict_proba generates the probability of that image belonging to a positive class. In this case, being classified as 1, since this is a binary classification. Oh, yeah, sorry.
I'm just curious, is the data set still archival? Is this something that people can still...
Yeah. You can see the code. The competition is closed, but you can see the code that, all of the codes that were submitted and the outputs. And,
what was the competition called, sorry?
Internal waves.
Then those outputs are saved into a CSV file, and as I mentioned, this code will be integrated into the existing code, will be trained with the new data set, and then the internal wave service will be available with near real-time updates. But as you might have noticed, all of our code right now is in Python, and actually one of the next steps includes moving the code from Python to Julia, because we are aware of the advantages of using Julia for training and inference. We have notion that it's ideal for intensive workloads, but also for projects that require scalability, that optimizes computational resources usage, which means that we're dealing with a potential reduction in time per iteration, which enhances training and also enhances inference. And we have, for example, here, one of the examples that happens currently with the Gilberto's code. In one of the outputs, there's a warning message about mismatched devices because of the CPU and GPU when running the XGBoost. And we know that Julia has packages that are libraries that are optimized for GPUs and inference on GPUs. So one of the next steps also includes this migration, let's call it, from Python to Julia. And now, João.
Hello everyone, my name is João Gonçalves. I work for Air Center. I'm currently the IT specialist and I'm also a software engineer. And I help the team to design a system where we have a data set of these Sentinel-1 imagettes that shows us the sea roughness. And the main challenge we had is we wanted to build a data set and we wanted to automatize as much as possible getting images in a fixed in a periodic manner. So we built a background service. This service periodically fetches the S1 vignettes show with the sea roughness from our defined sources. It uses the machine learning algorithm to identify internal waves, and then, as was mentioned before, it saves an internal wave. For every internal wave it stores, it also stores a negative image to give our data set some balance. And what we wanted to achieve with this is, so we have a growing data set. We have this automation to pre-label the data, and then we wanted to build an application that would let an expert and multiple experts in the future to help us verify these labels so we have the most accurate data set as possible. So for that, we've built an application. It was built with Go. This is a web application, and we wanted to have a user-friendly interface where we would show every data point in our data set and allow the expert to review the imagettes, analyze the sea roughness, and then confirm if if the label that was attributed by the ML model was accurate or not. So this is a very simple interface. We wanted to make it as simple as possible and deliver it as fast as possible. So we have, we wanted to make the life of the expert as easy as possible to navigate from one image to the next and validate a large number of images very quickly. So we built a very simple interface for that, where the expert can open a list. From here, we see that the interface is divided in several lists. The expert can select the list where there is unverified images, and then open one of them and click next, 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 and verify and confirm each one very quickly. So this is what we have done. This is the current features we have. We also created a web interface where we can see the positions on a global map of every internal wave event. Right now it's showing only the ones that were verified by an expert. And it's also possible to click on each event and see the sea roughness vignette. And in the cases where for a small area we have multiple vignettes, it's possible to select each one with the user interface. And this web interface, this map web interface, is continuously updated as soon as an expert verifies new data, confirms new data. So I've spoken about the features that are currently implemented already, but we have some features in the pipeline. Right now, we are working on multiple users, allowing multiple users to verify the labels in our images. And we are working on a consensus algorithm. It's still early stage, but the idea is that we want to have multiple experts logging in our application at the same time. Each one of them having automatically attribute to them a list of data vignettes for them to analyze and verify. And each one of them will give a vote with their sense of their verification, and then we will have a validation system that will use this consensus algorithm to basically check if there is a majority vote, and if there is, it marks the image as confirmed. If not, it still waits for more votes until it has either the minimum number of votes or has reached the consensus. And then this is what we are working on also. We want to have a way for experts to collaborate. We have, Adriana has already showed us some images where there is a lot of doubt, because some images are not easy to identify if there is an internal wave or not, and some experts might want to, add their opinions in a collaborative manner. So we want to give a way to add text comments from experts for every image, so a collaboration can be had. And then maybe it's easier to validate the data when there is a series of comments from experts, and maybe it will be easier to verify the most difficult cases. That's it from me. Thank you very much.